All right, greetings everyone. What I'm going to do in this video is continue with this idea of putting a Jupyter Notebook YouTube inside a Jupyter Notebook. In other words, there's no reason you can't talk about your Jupyter Notebook from inside your Jupyter Notebook as a YouTube, if you see what I'm saying. So what I'm going to do here is show you where I'm proposing. I mean, this is obvious really, but I put it on the Jupyter education list, educators using Jupyter notebooks, and I got some good feedback like, oh, that is a good idea, even though it is obvious. So then I'm going to take us right now to the EduSig. This is where I hang out quite a bit. You can find a lot of postings by me. I'm one of the two list owners of this particular list served by this time. And here in the month of November 2018, we have a lot of activity and excitement around whether France is adopting Python officially. I don't really know how the bureaucracy works over there and in what sense you need official stamp of approval for some language X to be accepted. Here in the U.S., it's kind of loosey-goosey. Every school kind of goes its own way, but then consensus builds and various associations and professional organizations make themselves felt in their influence. And here at the Oregon Curriculum Network, I'm one of those, quote, movers and shakers, ha ha, not really, in that I'm not big budget or anything. And these YouTubes, they're not super high quality, I admit it. They're just showing you possibilities and inspire you, another teacher, to do better. You can look at mine and immediately say, gee, I could do that and I could do better. So here on EduSig, I'm saying, well, if France is taking on Python, does that mean Jupyter Notebooks as well? And at the end, I link to Jupyter Notebooks, public listserv. I happen to be logged in as a Google person right now, so, but even if you're not logged in as a Google person, you can pop this up. And then I go through a link here to a Jupyter Notebook where I actually do talk about that Jupyter Notebook at the end of the Jupyter Notebook, and people say, it's not a bad idea. So that's what I did like a couple days ago. This time I want to talk about a different Jupyter Notebook, which I've just jumped to, called Generating the Face-Centered Cubic Lattice, which is kind of a home base in crystallography. It's one of several patterns that fill space, and we use XYZ all the time in high school and college math, sometimes to the detriment of exploring other scaffoldings or space-filling patterns. You could call them 3D tilings or whatever. Tetrahedron, octahedron together with twice as many of the former. The volume ratio of 1 to 4 is what we're looking at with Alexander Graham Bell and Octet Trust by Bucky Fuller. And of course, just generic crystallography, because it's the face-centered cubic lattice is what it's called. It's also called the CCP. So what we have here are four balls, and then like the dice number 5. You could think of these as dice patterns. 5 balls in the middle layer, and then 4 balls again at the top. So yeah, I got that right. I was about to say no, that's 6, but it's not a hexagon. It's like 5, right? And these balls all touch the center ball, if you can see that. It's kind of hard to see, maybe, but so it's 12 around 1, 4 plus 5 plus 4 equals, what, 13, right? And 12 around 1, that's also 13. This is the face-centered cubic lattice, another view of it. In the foreground, 2 12 around 1s. In the background, there's another CCP, or you could say IVM if you're into Bucky Fuller. The tetrahedron in the background is the same sphere packing. So in generating the FCC, I do something a little bit interesting. I use an alternative coordinate system called quadrays, which you can find in Wikipedia. A lot of people worked on this. I was one of the contributors. Several people will say they created them and invented them, and I don't say I invented them. So I'm not one of those people who says I invented them, but I do use them. And I find them interesting because those of us in the synergetics world, we're always getting kind of criticized because Fuller picks a fight with the XYZ people, and then he doesn't seem to offer anything else that you could call a coordinate system where you can do kind of numeric operations, vector addition, all the things that we're used to from XYZ. So this pops up as an interesting alternative. Think of it as 4 basis vectors from the center of tetrahedron, and immediately I'm in trouble for calling them all 4 basis vectors, because typically in linear algebra we'd say one of these is linearly dependent on the others, because you can always, reverse the vectors and do all this kind of stuff to get points in the opposite direction of a basis vector. So meaning I can get the vector pointing straight up by adding the 3 vectors pointing downwards, getting the results, and then reversing that. And so the negation is considered part of what it takes to build out to different points. And since you can do that, we would say the top vector can be considered dependent on these other 3. But if you don't allow rotation, and negation is a rotation by 180, if you're not allowing that as part of what it means to do linear combinations, you can only add in the positive direction. These vectors only have positive direction. Then you don't need negative numbers in your coordinates at all, but you do need 4 tuples. Okay, so we've divided space into 4 quadrants, and we can address all the points in space as linear combinations of these 4 vectors. So that's another link to the 4D meme that Fuller was so into. You could say the caltrop is the icon of this coordinate system as opposed to the XYZ jack, which is more of the so in this Jupyter note, more the XYZ way of doing it. In this Jupyter notebook, let me just run the kernel again and clear the output. So then I can go through it quickly. It'll take another 2 minutes to see this thing running. So let's see, at the very top, is there any code up here? First of all, I want to get linear combinations of these 4 basis vectors that point in the direction of the 4 spheres, the 12 spheres around a center one. Picture the origin at the center ball, and I need the 12 directions to the surrounding 12 balls. It turns out, if you do some computations, that these permutations of 2, 1, 1, 0 in quadrate coordinates will get you to all those 12 points. And I use some Python to make sure I've filtered out all but the 12 unique points of that pattern, and there they are. And then what I do to get layer after layer is I put like my cursor at the center of each ball in whatever layer I'm trying to go beyond, and I just create a ball at all the 12 positions around it per these vectors. So I do vector addition from every ball center, and in doing so I'm going to recreate some balls I've already have. In other words, inner more balls. I've already got the layers. As I grow outwards, I've already accumulated the inner more layers. And in doing 12 around every ball, I'm going to be hitting balls I already have. But since they all have integer coordinates, it's very easy to store them, you could say, in a database, anything with a unique primary key, such that balls we've seen before just don't go in. Only the new ones go in. So I use the equivalent of a unique database. The Python set is such a data structure, it won't allow duplicates. So I add everything, but what I end up with at the end of the day are only the new spheres per each layer. So when I run this code, it shows me how many balls it's getting as it goes through layer after layer. And these correspond to the sequence you'll find in the online dictionary, or encyclopedia of integer sequences. It's got this 1, 12, 42, 92, lots of mention of Bucky Fuller here, and also Coxeter, and also in the links section, myself, I think. Where is the links? Here we go. Blah, blah, Erner, yes, microarchitecture of the virus. So that's for another day to go down that rabbit hole. So let's finish generating the FCC. What I have to do then is convert all these quadrays to XYZ coordinates, and I have algorithms to do that because POV-ray does not understand, of course, quadrays. So I'm generating scene description language that looks kind of like this behind the scenes and running it through a ray tracer so that I can get more balls. This is like 3 layers. Actually, it's the nuclear sphere surrounded by 12, surrounded by 42. So we'd call this a 2-frequency packing. And I continue to apply the same algorithm and start up a pandas data table. Now, I won't go into great detail on how we do this, but in pandas you can have, okay, so it crashed there because I skipped running the cell above it. You got to run these Jupyter cells in the right order if you expect things to work. So I'm creating a pandas data frame, so-called, and I'm going to use what's called a multi-index. So that going across in the columns, I can have both XYZ and quadray coordinates. So I call that coords. And then going down the side, I can have the different layers of this VE, or what we call a cuboctahedron. So here's that table. See, it's quite complicated because it has what's called a multi-index. Going across, say, layer 0, here's the origin. XYZ and quadrays, all the coordinates are 0, A, B, C, D. We'll call that ball 0. Then ball 1 through 12, this is layer 1. And you can see the XYZ and IVM coordinates side by side. And then I continue with my algorithm, getting layer 2 of 42 balls. So you see all the way down to, let's see, layer 2 starts from, so 42 plus 13 is 55. So layer 2 takes us all the way to 54. So 13 through 54 is the next layer. And then we keep going. This is what we call 3-frequency. You count the intervals between balls along every edge to get the frequency. And here's 4-frequency. So this is the actual code that I use in the Jupyter Notebook to generate these POV-ray scene description language things. There's even an embedded YouTube about, just showing me rotating one of these ball things in a 3D CAD program. What I'm going to do next, though, is take this video after I edit it a bit and stick that in here too. So thanks for watching, and hope to see you in a next video pretty soon.